full professor. Before that, he was a postdoctoral researcher at Sandia National Laboratory. And before that, Center for Turbulence Research, Stanford University. Which is, well, at least it used to be a very nice place.
It still is.
I thought they stopped funding it now.
They might be, yeah, they might be.
And he is Associate Fellow of AIAA. And I don't want to drag this on too much. He has about 60 publications, highly cited. So today he's going to talk about the advances in high fidelity simulations toward fundamental combustion research.
Thank you for your kind introduction. Good afternoon, everyone. So this is my final schedule of this fairly long journey, so I hope I'll still keep my energy up to entertain the audience. I don't know how many of you were here with during my previous visit in October. So having that in mind, I try to switch the subject a little bit, so that I don't have to repeat the same stuff over again. All right. So first of all, again, as usual, I would like to acknowledge a lot of members in my team at the co-PI level, as well as my students. Some of the presentation are sponsored by a number of different NSF and DOE projects that I've been working on for the past 10 years. I also like to acknowledge DOE computing resources where all these computations are done. And last but not least, all the brilliant students I've ever had, I had in my faculty career, the couple of current students as well as the former students. Well, this is a group, I understand that I don't have to convince the importance of combustion research, but let me just try to briefly point to a couple of key points here. This is the data from the World Energy Outlook, some fresh version. It just came out last November. The key point on this slide is this is a kind of projected global energy demand trend. And these pink and brown lines indicates including the gas. All these are typical fossil fuel resources, and they are not in a high decline. Even the petroleum is still expected to be declining a little bit, but not by much. And this is the fractional contribution. But the primary energy demand globally is projected to grow by 40%, which means actual usage will increase over time, even way up to 20, 30 some more years. So message is clear that oil will continue to remain as a leading fuel, while everyone knows that there is more potential use of natural gas in the near future. So still, petroleum, combustion, and all these fossil fuel will remain. And what's also interesting is that all this Middle East and North African region is set to supply the majority of this additional demand in oil up to 2035. So Saudi Arabia is way on top here. So again, that makes it all the more interesting for everyone in here that we are right at the core in the place to continue to work on high efficiency combustion systems. So basically, there's clearly strong drivers for developing further advanced combustion systems. Again, there's some kind of bad news that was found out over the last year. The CO2 emissions, despite all this discussion of global warming, has rebounded to record high. So maybe gas prices went down, and whatever the reasons, so things are getting worse. So that really reminds us that we really need to make a big effort to improve the situation. Energy efficiency also was getting worse, and spending on oil imports is nearly record high. So suddenly there's a big turnaround that people maybe perhaps forgot about all these issues, and things are getting worse. So there's a continuing demand to develop better high efficiency combustion systems, And based on my experience, my research expertise, high fidelity predictive simulation, we are trying to make that to be amenable to speed up the turnaround of the development of those advanced combustion systems. So my research primary effort has been direct numerical simulation. The word direct, once again, I re-emphasize to everyone that brings up question about that. This historically comes from the turbulence simulation community. The word direct means we are not using any subgrid scale or statistical averaging of the turbulence model. So in a way, we are solving for direct continuum level Navier-Stokes equation without any modeling effort. When it comes to combustion, chemical kinetic reactions are by nature not in a continuum level. So that is an approximation. So in that way, it is not real first principle simulation from the chemistry point of view. So but that's the basic context of the terminology here. High fidelity simulation is great. The computer power has advanced a lot. Nevertheless, just the sheer scale of physical and the length and time scale is still so huge. It spans over 10 decades. If you think about all the elementary chemical reaction time scale all the way to the device time scale. And this is what we kind of project to be covered by the current state-of-the-art DNS, which spans quite a bit, but still it's not enough to cover the whole range. So even that is going to be very, very expensive if you really want to do a multi-D, 3D simulations. And what added insult to injury is that the number of equations become very, very large if you want to simulate with the realistic the fuel. This shows a trend taken from Tianfeng Lu. The recent trend of the mechanism development done by a lot of those chemical kinetics. We are developing all the way to C16 these days, and the number of species are thousands and number of reactions are tens of thousands. So this is enormous. You just, in addition to your Navier-Stokes equation, you have to add that many the transport equations into a system, which makes it incredibly expensive. So there is a still strong need, as much as we want to develop real high fidelity, accurate reaction rate and chemical mechanisms, by the time you really want to apply that into your DNS, we still need to reduce it down to a amenable level. So there's still active research effort going on in that area. If you want to do further to predict some pollutant formation, more in particular the soot formation, that alone is another whole new can of worms, and that requires a very complex chemical description. Not only a gas phase formation of the PAHs, but also those additional soot growth model needs to be implemented. This was a subject that I covered last October, so I think I'm going to keep it to a little bit relatively simple level this time. So direct numerical simulation of combustion has been around for a few decades, and it has already come a long way. Once again, the basic principle is we would like to resolve all the continuum level details. So since the accuracy is really important, we try to take a very good care of the computational methods involved in that. The premise of DNS is that since you have full access to temporal and spatial resolved information, it serves as by itself as a numerical experiment database. So you can actually explore, investigate all these databases to understand exactly how things evolve in time and what are the interactions between turbulent eddies and your flames and so on. So those are really kind of fundamental science study itself. But also in addition, the DNS is really expected to play an important role in developing physical combustion submodels that can be really utilized in the engineering level commercial code for CFD simulations.